Today, we're going to take a fascinating journey deep into the mind of artificial intelligence, but not to figure out what it's thinking. We're going to look at how it's actually built, and we're going to see how we went from building these things like handcrafted machines to something much, much weirder.
All right, let's just jump right in with the biggest question of all. How do you even begin to build a brain? I mean, for the last decade, this has been the problem obsessing AI architects. Do you design it like some perfect, intricate clock where every gear has its place, or is there another way entirely?
Think about it this way. The old way of doing things, traditional coding, is all about being a micromanager. You write explicit rules. If this happens, then you do that. Every single possibility is spelled out. But with neural networks, the philosophy is the complete opposite. You don't build the final machine. Instead, you create a space, kind of like a computational playground, and you just let the learning process figure out the rules for itself. And that right there brings us to the core idea of this whole explainer, the scaffold hypothesis. This is so crucial. The point is that great AI design isn't about engineering some perfect, finished product from the get-go. No, it's about building a flexible framework, a scaffold, that the training process can then use to climb and adapt and build on in ways you never, ever could have predicted.
So, here's our roadmap. We're going to start in the past, when these models were built completely by hand. Then, we'll get to the massive breakthrough of the first reusable blocks. From there, we'll see how a universal language for AI has started to emerge. And finally, we'll look at where we are today, designing entire grammars for intelligence, and what that means for what's next.
So let's rewind the clock, back to the beginning, to the era of these bespoke, handcrafted models, where every single network was like a custom-built car, a total one-off creation. So in 2012, bam! AlexNet comes along and just changes the world with its totally custom architecture. But then, just 2 years later, a new model called VGGNets shows up. And it planted this little seed of an idea that would end up changing absolutely everything. The simple yet powerful idea of repetition. You see, the folks who designed AlexNet had a very strong opinion about how vision should work. They thought a network should see big, blurry shapes first, and only then focus on the tiny details. So they literally built the architecture to force it to work that way. It was a really rigid, top-down approach that basically hard-coded a human belief right into the silicon. Then VGGNet came along and just threw that whole idea out the window. It asked this really radical question. What if we're trying too hard? What if the secret isn't to be more clever, but to be simpler? What if we just take one simple, kind of dumb building block and just repeat it over and over again? And this right here was the first real step away from custom engineering and towards a modular, compositional way of thinking.
And that little idea, it wasn't so little. It led to the first true revolution in AI design. This is the moment when the whole scaffold hypothesis stopped being a theory and became real, all thanks to the invention of a single, brilliant, reusable block.
This is it, the residual block. It's the heart of a model called ResNet, and the idea behind it is so simple it's almost funny. You take your input, let's say an image. You compute some small change, a little refinement for it, and then you just add that change back to the original. You don't replace the information, you just add to it. That's the whole trick.
And this quote just nails the paradigm shift. The entire field stopped asking, okay, what big, complex job should this layer do? And they started asking, what small update, what little refinement should this layer add to the mix? It's the difference between trying to paint a whole new picture from scratch versus just adding one perfect brushstroke.
And here's where the magic really happens. Seriously. Even though every single block in this network started out completely identical, the training process taught them to specialize. The early blocks, they learned to see basic things, like edges. The middle blocks started combining those edges into parts like an eye or a nose or a wheel, and the layers at the end, they put it all together to see whole objects. This wasn't designed by a human. It just emerged.
That breakthrough with ResNet, it basically kicked the door open for the next great leap. And what came through that door was the Transformer era, where one single building block would go on to dominate the entire world of AI. So, say hello to the Transformer block. This is the new king of the castle. It's like the ultimate Lego brick for AI. It's built from a couple of key parts, but crucially, it's held together by those exact same residual connections we just saw in ResNet. And it turned out this one little block was good at, well, pretty much everything. And when I say universal, I am not kidding. The way we build today's most powerful models is literally by stacking this exact same block dozens and dozens of times. Look at this. GPT-2 used 48 of them. GPT-3 used 96. Llama 3 uses 80. The path to making AI smarter wasn't a more complicated design, it was just more repetition of the same simple scaffold.
But the ultimate proof, the real aha moment for the scaffold hypothesis, came when researchers took a look inside a model called BERT. What they found was stunning. Just like in ResNet, the identical layers had taught themselves this incredibly clear hierarchy. The first few layers learned basic grammar, the middle ones learned the actual meaning of words, and the top layers? They were figuring out complex relationships across sentences. Again, nobody told them to do this. It just emerged.
And that brings us right up to today. The focus has completely shifted. The top AI labs aren't really trying to invent one perfect giant model anymore. Instead, they're designing something much more abstract. They're designing languages or grammars for building them.
Modern AI design looks a lot like this. It's a component library. It's like ordering from a menu. You don't have to invent a new attention mechanism from scratch. You just choose the best one from a list of proven options, like grouped query. You need a normalization layer. RMS norm is the top choice. It's less about being an inventor and more about being a chef, picking the best possible ingredients. So the big result of all this is that a state-of-the-art model like Llama 3 isn't some mystical, magical creation. It's a recipe. A simple and elegant recipe made by picking the best components from that library, putting them together, and then just stacking that block 80 times. That's really it. So, after this whole journey, where does this all leave us? What have we really learned about how to design intelligence? And what does it tell us about the future?
Well, it seems like 4 key principles have really emerged. 1. Simple, uniform structures are the only way to get to massive scale. 2. That residual structure, adding information instead of replacing it, is absolutely fundamental. 3, and this is a big one, you have to give specialization the space to emerge. You can't force it. And 4, the best designs are built with components that are swappable, just like parts in a machine.
Which leads us to this really profound final thought. The game has totally changed. We're not really building neural networks anymore. We're designing computational languages, grammars, and the whole process of training an AI? Well, that's just the machine writing its own incredibly complex program, using the language that we gave it.
And that leaves us with the most exciting question of all, right? We've found a couple of these powerful languages of computation, but what new grammars, what new scaffolds for building intelligence are still out there, just waiting for us to discover them?